Hi, I'm Alistair, and if, like me, you love escape room games, you'll probably be familiar with one of these. This is a directional padlock, and unlike a regular padlock that's unlocked with a key, or one where you enter a numeric combination, this one is unlocked through a sequence of directional movements, up, down, left or right. And these are very popular in escape room games because they provide a bit of variety from other sorts of locks, and also because there's lots of puzzles that can resolve to give a sequence of directions. So anything involving a map or any sort of navigational instructions, for example. Now the problem is that Masterlock, who invented this padlock, have decided to discontinue it. And because the mechanism is quite complex and Masterlock still own the patent on it, it's unlikely that any other company is going to be able to bring a similar directional padlock to market anytime soon. So what does that mean for escape rooms? Do they have to ditch all of their puzzles that resolve to a sequence of directional movements? Well, no, but they just need some other sort of locking mechanism into which that sequence can be entered. So in this video, I'm going to demonstrate a couple of different examples that I've come up with. And because I'm not constrained to having to fit into the form factor of a padlock anymore, I can also theme them to match some common escape room scenarios. So the first example I'm going to demonstrate is this pirate themed directional lock. So you can see I've got a compass rose, and around the points of the compass I've got metal touch points at each of the cardinal directions. Then I've got a maglock on the side here, and that is securing this key in place. So what players need to do is they enter their directional sequence by touching the appropriate points on the compass. And when they do so, a sound effect plays that lets players know that their input has been registered. Now the correct sequence for this puzzle has been set to north, east, west, and then south. And when the correct sequence is entered, the maglock releases and players can retrieve the key. Now, just to show you how this works, if I flip it over to show you the internals. So we've got an Arduino here, and this Arduino is monitoring 4 touch sensors which are positioned in a 4-directional shape here. And if I put my finger on the reverse of the board, you'll see that these actually light up. So these are sensitive enough to be able to detect touch input even through the wood I'm using. This is 3.5mm plywood, I think I've got here. So those inputs are detected by the Arduino, and that triggers sound effects through the serial MP3 player here, which goes to this amplifier board and a speaker in the middle. And also it sends a signal to this relay module here, which controls the 12-volt power supply going to the maglock. Now, I will demonstrate this wiring in more detail when I show you a wiring diagram later, but what I want to really draw your attention to is that this same basic setup here and the same code running on the Arduino can be used in many different scenarios and customized to work in slightly different ways. So here's another example, and this time rather than a pirate theme, I've gone for a kind of space aesthetic. So I've got a joystick which I've mounted to a panel that I've just painted silver, and I've also got an LCD screen up here that says navigation data and a prompt. And to enter the directions into this lock, instead of pressing points on a compass rose, players have to push the joystick into one of 4 directions. And instead of having the sound effect to let them know when they've done that, you can see that there are LED lights that illuminate, and also the LCD display actually gives a complete sequence of directions that they've entered so far. Now, another change from the pirate puzzle is that instead of automatically unlocking as soon as the correct sequence is entered, players actually need to explicitly say when they think they've got the sequence correct and submit it. They do that by pressing this red button on the top. Now in that case that sequence was incorrect, but if they enter the correct sequence first, which is up, up, down, down, left, right, now when they press the button on the top, you can see the maglock ejects the catch as before. So it's slightly different behaviour to the previous example, but if I turn this over to show you the reverse, you should see that actually component-wise it's still largely the same. We've got an Arduino, and the Arduino has 4 inputs for each of the 4 directions. The difference is that this time they're these micro switches that are wired around the joystick controller. And we've also got the LED lights, which you can see illuminate there. Those are also connected to the terminals of these micro switches. Then we've got the relay that's controlling the power to the maglock, just like before. We've also got the LCD display that's wired to the I2C output of the Arduino. Now, the thing is that the sketch running on the Arduino is exactly the same as the sketch that was running for the pirate puzzle. And the way I've coded it, and I'll show you that in a moment, is that these optional outputs, whether you want the visual display, whether you want the sound effects, and whether you want the puzzle to unlock automatically or whether you require the player to actually submit it, those are all things that you can change in code. Now, if you wanted to create a directional puzzle that was a centerpiece in your escape room game, you might want to go for something a bit larger, like this. This is a dance platform for a Dance Dance Revolution arcade machine. But internally, it works almost exactly the same way as the 2 examples I've just shown you. If I open it up, I can show you how. So now that I've removed the metal plates that were holding them in place, I can take one of these directional pads off and show you what's behind it. So very simply, this is a 3mm acrylic that has got some aluminium foil stuck to the back of it. And then on the board itself, we've got this conductive strip that's been arranged into a comb pattern. And what happens is when you press your foot down on the pad here, it presses the foil down, making a contact between these comb patterns that are very close together and closing a circuit. So this is a very simple pressure activated touch pad. The wires that are going here, by the way, that's actually just to power some LED lights that are mounted around the outside of the plate and make it light up, just to confirm that entry has been registered. They're not actually required for the touch switch at all. That's these 2 wires that are going to the plate here. So this is really very, very similar wiring to I showed you in the previous example. It's just some touch sensors, some LED lights to provide visual feedback when they've been detected, and you could use this as a directional input, just like in the other examples. So to explain the circuit I've been using in more detail, let me show you a wiring diagram of the components in Fritzing. So here in the centre of the diagram I've got an Arduino Uno, but this could be a Nano or other Arduino or any ESP board. There's nothing in this project that's particularly specific to any one microprocessor. And then on the left hand side here I've got my directional inputs, and then I've got various outputs that the microprocessor is going to control. So we'll take a look at each of these in turn, starting with the inputs. So here I'm showing momentary push buttons, which is what I was using on the joystick, and it's also what you'd find behind most push buttons that are mounted on a console. So they have 3 contacts: a common terminal, a normally open terminal, and a normally closed terminal. And often when we wire switches, we only use 2 of those contacts. So you use the common pin and either the normally closed or the normally open pin. And when you push the button, it either makes or breaks the connection between the 2 pins you're using. So a normally open pin will have its connection made on push, whereas a normally closed pin will have its connection to common broken on push. But here I'm wiring to all 3 terminals, the common, the normally open and the normally closed. So the LED here is wired through to the normally open terminal, and then on the other leg of the LED I've got a 220 ohm resistor that's going to 5 volts, and then the yellow wire, that's going through to the normally closed contact, and then each of those wires is going to a unique GPIO pin on the Arduino. and I've got the common terminal wired through to ground. So what's happening here is that by default, when the button is not pressed, the normally closed terminal, so that's the one that's going through to the GPIO pin here, is connected to ground. So this is going to read a low signal when the button is not pressed. And when the button is pressed, that's going to have that connection broken. And if we activate the internal pull-up resistors on these GPIO pins here, that will make the signal jump to a 5-volt high signal. So we can tell when the button has been pressed, because the input on this pin here is going to jump from 0 volts to 5 volts. Now at the same time, however, the normally open pin, which was wired to the LED here, so this had one of its legs wired through a 220 ohm resistor to 5 volts, but the other leg wasn't connected. But now when the button is pressed down, this normally open contact is going to be wired through to the common terminal instead, and now it has a path through to ground. So current can flow from the 5 volt through the resistor and LED through to ground, and that's going to cause the LED to light up. So sometimes you might see Arduino code that has a light that lights up when a button is pressed, and what you'd do is you'd use digital read to test whether the button has been pressed, and then if it has, you use digital write to write to the LED to turn it on. But if you use a wiring pattern like this, that code becomes unnecessary. The LED is lit purely through the same physical action that you did to press the switch. It will be changing the voltage that's read on the GPIO pin here, and also allowing current to flow through the LED just by pressing each of these buttons in turn. So that's going to give us a visual feedback when each button is pressed. Now down here I've got my LCD display. Now you can get lots of different sorts of LCD displays. Some of the basic models have a whole lot of terminals across the top here that need to be wired and use up lots of pins on your Arduino. But what I recommend using is something called an I2C backpack. So that's a little additional daughter board that's slotted on the back of the LCD, and you can buy them with these already fitted on. And that means that you can control the LCD display just through 4 wires in total: ground, 5 volts, and a data and clock line, which are a standardized I2C interface. It just makes the wiring much more straightforward than attempting to wire to each of the data pins individually. Now the I2C interface on an Arduino always uses pins A4 and A5. A4 is the data line, A5 is the clock line. So I've got those wired up here. Just to point out, so the button inputs here, these can use any pins at all. I've just used A0 to A3 in this diagram here, but they could really be anywhere you want. And then over this side here, this is our MP3 player. This is a board I've used quite a lot in recent projects. Similar to a DF Play Mini, if you're familiar with those. I just find them slightly easier to use because their power requirements are typically a little bit easier to meet, because they're very simply wired to ground and 5 volts again. And this also simply has 2 wires connected to it, but this time it's a serial data connection, and I'm using the AltSoft serial library to supply data to the MP3 player, and that always uses pin 8 for receive and pin 9 for transmit of serial data. So pin 8 is receive at the Arduino end, so that gets wired to transmit on the MP3 player, and pin 9 is transmit, so it gets wired to receive on the MP3 player. And then it has an output up here, which is a 3.5mm audio jack, so you can take that output and wire it to an amplifier and then to a speaker up here, so you can actually hear the output. And then over here, this is the thing that really makes it a directional lock. So whereas the audio and the visual feedback are completely optional, you really need the components down here if you want this to function as a replacement for a Masterlock directional lock. So I've got a 5 volt relay module, once again connected to 5 volt and ground, and it has a signal line which I'm using digital pin 2 here to connect to. When that has a high or low signal written to it, that will, on the load side of the relay here, that will cause the common terminal to switch between normally open and normally closed. So rather like the button inputs here, we had an input that was going between normally closed and normally open. Here we've got an output that is going between normally open and normally closed. And on this side here, we've got a 12-volt maglock with a 12-volt DC supply, and that circuit there is being interrupted through the relay module, so we're able to control power to the maglock by turning the relay on and off using this digital pin here. And just for contrast, this is the circuit diagram of the pirate compass example I demonstrated. So it's very similar. The main difference is that instead of using the momentary push buttons for inputs, I've got these capacitive touch sensors instead. And these use a TTP223 chip, which needs to be powered. So for that reason, these are supplied with ground and with 5 volts. And then they provide an output through these yellow signal lines, which again I'm connecting to pins A0 to A3 on the Arduino. Now, because these don't have the normally open and the normally closed terminals that the momentary push buttons did, I can't wire an LED in series with them in the same way that I did with the earlier example. They do actually have an LED on the board, and you could expose that if you wanted to use that as visual feedback for when the buttons have been pressed. Or alternatively, you could wire some standalone LEDs onto this side of the board and have them turn on when the associated input has been detected. Other than that, the rest of the wiring here remains the same. So now let me show you the script that's running on the Arduino, and this might seem quite long, but that's mainly because I've tried to comment it quite extensively. There's nothing actually that complicated here, so we'll just step through it from the beginning and I'll try to explain what's going on. So starting at the top, I've got some defines here. I've got one called auto check, one called use audio, and one called use display. And I mentioned that there's various aspects of behaviour that you might want to customise with this lock. So you might want to have the lock automatically open as soon as the correct sequence has been input. You might not. You might want there to be audio sound effects that accompany each direction that's pressed, or you might not. And you might have a display that actually shows players each direction as they input them. And for each of those things, there's extra sections of code that needs to be included. But if you don't want to use those features, you might not want to have that code being executed for no particular benefit. So what I've done is I've defined 3 different statements here. These are called preprocessor definitions. And what that means is that at the point that you compile the code and upload it to your Arduino or other board, depending on which combination of these 3 features you include, the sections of code which I've got later, so this section here will only be included in the compiled code if you want to use the display. This section here will only be included if you want to use the audio output. So they won't be occupying any memory on the board, and they won't be occupying any processor time actually executing functions that have no benefit, because they'll be stripped out by the compiler before the code is even sent to the board. So that's why I've chosen to define preprocessors rather than an if statement that tests the value of a variable. So I've got 3, and they relate to those 3 different behaviours which I mentioned. So this one defines whether the sequence is automatically checked. This one is whether we want to have audio output going to a serial MP3 player. And this one is whether you want to have the LCD attached. And you can use any combination of them on or off. To use them, you simply uncomment the lines like that, and to turn them off, you comment them back again. Okay, then we go on to the include section. So this is where I include external libraries which have already been written, which provide some functionality that we want to use. So I'm using the bounce2 library. I've used this lots of times before. Whenever you have any mechanical input, like push buttons, this will make sure that you don't accidentally get double presses detected, and that's obviously going to be really important if players are entering a sequence that might have the same direction pressed twice in a row, you want to make sure that you're not accidentally recording that when they actually just wanted a single press. If we are making use of audio, then I'm going to use the AltSoft serial library that provides a software serial interface that will send commands to that MP3 player. And then I'm also going to use this YX5300 library to actually send the commands to the MP3 player. If we're using the display, well, that uses an I2C interface. So for that, I'm going to use the wire library that comes with Arduino. And then I'm also going to use this library here, which provides functions to send output to the display. So in both of these examples of audio and display, I'm using one built-in library that is installed through the Arduino IDE. So you go Sketch, Include Library, Manage Libraries, and then you install AltSoft Serial and Wire and Bounce to that way, and that's why they're then included in angled brackets. But for the specific libraries for the hardware I'm using, so this one here and this one here, those are stored in a local subfolder for this project, which is in the source subfolder. So I'm including those in speech marks like this. And you can download the source and view more information about those libraries at these GitHub links here. So again, I'm using this if def. So if defined, this means use audio, which is what we defined up here, including these libraries. If def, use display, include these libraries, and we're only going to include the ones that we're actually going to make use of the functionality of in the code. Then we go on to the constants. So the constants are variables that are not going to change throughout the duration of the project. And the first thing I'm going to do is I'm going to create an enum. So an enum is a way of declaring the values that a particular variable can take, rather than having an int 0, 1, 2, 3, or a char, or a boolean, or something like that. An enum lets you define arbitrary words, essentially, that will get mapped to values. And it's a useful way to be able to refer in your code to directions as down, right, up, and left, for example, rather than using numbers 0, 1, 2, 3 and trying to remember which one is up, down, left, and right. An enum is a useful way to assign labels to values. So we've got 4 directionals. I'm going to call them down, right, up, left, but you could also call them northeast, south, west if you wanted to. And I'm also going to create an array of characters which I'm going to use when I want to print those states to the LCD screen, or if I want to print them to the serial monitor. So here I'm just going to give them each a single character code, DRUL, for down, right, up, left. So this is these are the names that we'll use to refer to them in the code, whereas this is the names that will be used to refer to them when they're printed out. The reason why I've only used a single character for each one is so that then when I print the string of directions onto the LCD display, I can fit more on the display. If I actually tried to write out the full names, that's a 16 by 2 character display, so I'd only probably be able to get 3 directions on there before I ran out of room. So that's the very simple reason why I've only used one character for each string here. Then we say the GPIO pins to which each of these directions are attached. So I'm listing them in the same order. So the down button is connected to pin 4, the right button is connected to pin 5, up 6 and left 7, for example. In the wiring diagram, I think I was actually using pins A0 to A3. In the code here, which is one that I've actually got running on the board, it's 4, 5, 6 and 7. These can be any GPIO pins you want that are capable of receiving a digital input. So adjust these as you see fit. And then if you are not using the auto check function, so notice there's an N here. When we were using the conditional including the libraries at the top here, we're saying if def. Here I've got if n def. So if auto check is not defined, that means that we want players to manually have to press a button when they think they've input the correct sequence and they want it to be checked. So in that case, we also need to say the GPIO pin that that button is connected to that we want them to have to press. And we'll call that submit pin. We've then got a relay pin, so this is going to be the output that is controlled to open the lock if the sequence is correct. And then we also need to define what the sequence that players need to enter is. So how many steps does it have in the sequence? And we explicitly set this because if we are using the auto check feature here, we need to know after how many steps the code needs to wait to check whether the sequence is right or not. So we need to tell it that we're expecting a total of 8 directions, and those 8 directions are going to be taken from the enum values here. So the solution I've got programmed at the moment is up, up, down, down, left, right, which will be familiar to many of you as the Konami cheat code. But you can set this to anything you want, and if you add more directions here, if you take more away, you simply need to update this number here so that it reflects the number of elements in this array. Then we go on to the globals. So globals are variables that are shared throughout all the functions in the code. And I'm going to create an array of bounce objects. So bounce was this library that we included at the top, and that's what I use when I want to read any mechanical inputs from buttons. So rather than doing a simple digital read of the pin to which the button is connected, what we'll do is we'll create a bounce object, attach it to that pin, and then we'll use the debounce functionality of this object to tell whether it's been pressed or not. And that will help just get rid of any noise that there might be on that signal pin that we'd have got if we'd read it directly. So we've got an array of 4 directional switches, one for each of the directions. And then again, if we are not using auto check, we also need to have a bounce object for the submit button that they press when we want to check their sequence. We need to keep track of what position of the sequence players have got up to at the moment. So this is a 0 based index, so we'll always start at 0. And then for each direction button that is pressed, this is going to increment by 1, just so we keep track of where we are in the sequence. And then we've got some more conditional code depending on the features that we want to use. So if we're using audio to play a sound effect when a direction button is pressed or when the puzzle is solved, for example, we're going to create an instance of the AltSoft serial object. And we don't need to specify any parameters as to what pins that is running on, because AltSoft serial on an Arduino always uses pins 8 and 9 for receive and transmit. And then we'll create an MP3 object, so that was provided by the specific library that I included up here. And that's the one that knows about the controls to play and stop and pause and resume MP3 playback. So we'll create that, we'll call MP3, and we'll point it at the software serial interface that we just created. Now, if you're using an Arduino Mega, that actually has more than one hardware serial interface on the board already, so you don't need to include the alt serial here. What you could do instead is you could point this at serial 1 or serial 2 or serial 3, for example. But I'm assuming you're using an Arduino Uno or an Arduino Nano board, which are more common, and they only have the single built-in serial interface. So that's why we're using the software interface for the MP3 connection. Now, if we're using the display, well, in that case, we need to create an object to be able to access the display. So I'm calling that LCD. And for this, we need to pass in the I2C address that is being used by the display controller on the back. Now, I2C addresses need to be unique, and generally they're assigned by the manufacturer. You can't have 2 I2C devices on the same bus that have the same address. So some display boards and some other I2C devices let you choose the I2C address that they use by a series of jumpers on the back. Now, I looked through all of the boards which I've got, and they all used one of 2 addresses. They're either 27 in hexadecimal or they're 3F. So I suggest, if you are unfamiliar with using I2C, I suggest you try using one of those two addresses first. If neither of them work, then there is a script called an I2C scanner script which you can download, and what that will do is that will loop over all of the possible I2C addresses and just try essentially pinging every device on every address and seeing if anything comes back, and it will print it to the serial monitor. So that's a useful kind of helper script that you might need to make use of if you can't find the I2C address of a device that you've got connected. But generally speaking, for the LCD displays of the type that I'm using here, all of mine have used one of those two addresses assigned by the manufacturer. If you do have another device on your bus that's already using one of those addresses, normally you can, like I say, either bridge a little solder gap on the board or possibly a jumper that will increase this by 1 or 2 either side of that base address. So that just needs to be specified in the constructor to the LCD object there. And we're also going to have a little Boolean flag to say, has the input that the player provided been correct for every stage on the way? And this is actually a change that I put into the code relatively late on. To start with, what I did is I checked each input that the player made as they went and compared it to the input that we'd expect for this point of the sequence based on the current step that they're up to. And as soon as that sequence differed from the correct sequence, then I informed the player that they'd gone wrong. But that actually kind of gave away too much information because it let them know, among other things, how long the overall code was and also the point at which they went wrong along it. And through trial and error, when you've only got 4 possible inputs at each stage, it actually wouldn't take too long to brute force the correct solution. So what I do now is I introduce this new variable here that basically keeps track in the background whether at any point the sequence that was entered went wrong, but I don't actually act upon it until the point when we come to check whether the input was right or not. So players are not given any additional information as they're going, whether they've gone wrong or not. It's only at the point that their sequence is actually tested that we look at this variable here and see whether they got it right or not. So you'll see how that's used a little bit later on in the code. So then we go into the setup function. So setup is called once when the program first starts running. I create a serial connection. This is the hardware serial interface on the Arduino. It's not actually being used to control any devices in this sketch. It's simply being used for outputting debug information back to the Arduino serial monitor. So if you turn this on here, you'll see some extra debug information, which is quite useful to check that the code is running as expected. And I also output the file name and the date at which this code was compiled. Again, if you've seen many of my tutorials in the past, you'll see that this is a pattern which I generally now adopt in all my code, because it's just very useful to see when you first plug in a controller what script it's running and what version of that script it's running as well. We set the pin modes for all of the pins we're using. So our input pins, we've got our 4 directional pins. We'll loop over those in an array, and we will attach the 4 debounce objects that were in our dial switches away up here. So we've got our 4 bounce objects here. We will attach each of those to the corresponding directional pin, and we will activate the internal pull-up resistor on each of those lines as well. So when those pins are not connected through to ground, they will read a high signal because they're being pulled up through this resistor here. And when the switch is pressed and they are pulled through to ground, this will read a low signal. We'll also attach a bounce object to the submit button if we are making use of one. So again, we'll just wrap that in this preprocessor check here. And we'll initialize the output pin, which we're going to use to activate the relay. Now, if we're sending audio files to the audio controller, we need to do a bit more initialization here. We'll start the software serial interface. So again, remember this one at the top here, this is the hardware serial interface for the serial connection to the PC. This is the software serial interface which we'll use to send commands to the MP3 player, and we'll initialize that at 9600 bits per second. We'll start the MP3 controller and we'll specify what volume we want the output to have as well. You'll need to send this to an external amplifier anyway, so the exact volume value you set is not too important there. And if we're using the display, well, in that case we need to do some additional initialization for that as well. So we'll start up the I2C interface here, and we will just send effectively a test transmission to the LCD. So we'll begin a transmission to the address which we specified was used by the controller, and if we can end that transmission with anything other than a positive value. So basically when this end transmission returns a 0 if no errors were found, otherwise it returns an error value essentially. So if we get that back and it was a 0, that means that we found the LCD and we can then begin the display, tell it how many columns and rows there are, turn the backlight on and print some data onto the top line of the display. If end transmission returned value anything other than 0, then we know there was a problem with initializing the interface to this address, so we'll print our debug information that the LCD was not found there. And then you can go away and check your hardware connection. So it's possible you've got the data and the clock line the wrong way around, or perhaps power hasn't been supplied correctly, something like that. Then we go on to the loop function. So the loop is a function that actually does all of the main program logic. Once everything's been initialized, it just goes round and round forever for as long as the Arduino is powered up. And what we do is we loop over each of our 4 input pins, so each of our 4 directions. We update the bounce object that has been attached to each of those directions, and that's going to keep track of whether they've been pressed this frame or whether they have already been held down or whether they've been released, things like that. And in this case we want to act when the value that the switch has risen. So that's gone from ground to 5 volts to a high voltage. If that's happened, that just means that the button has been pressed. If we are using audio, we'll play our first MP3 file from the SD card here. If we're using the display, what we'll do is we will print on the second line of the display the direction that was just entered. So just to explain this a bit more here, the set cursor function, this lets you move the cursor at which text will be printed on the LCD line to the X and Y position specified here. So when current step is 0, which is when we've just started off, we want to print at the 0th position along and the first line down. So that's going to be the first position on the second line of the display basically. And what we print there is the dir str, so the string of directions, which you'll recall was all the way back up here. Here we go. This was the sort of the friendly names that we had to refer to each of the directions that could be entered. And we want the element from that array that corresponds to the button that was pressed. So what we've got here is we look up the ith index because we're looking through all I buttons from 0 to 3, and that will print the name of the direction that was just pressed onto the bottom line of the LCD. And we'll also output that information to the serial monitor as well, whether you're using the display or not. And what we need to do now is check whether the direct button that was just pressed was the correct button or not. So we will compare I, which was the index of the button that was just pressed, was that the same as the current step that we're up to in the correct sequence. And if it was the same, well, there's not really anything to do here, so I'll just print to the serial monitor that was correct. If it was incorrect, so if the index of the button that was just pressed is anything other than what we were expecting for this point of the correct sequence, that's when we set our input correct flag to be false here, but we don't immediately tell the player that they made a mistake. We only do that when they've actually reached the full entry of the sequence or when they press the submit button. All we do is we set the flag, and what we'll do is we'll print some debug information as well. So we'll say that it was wrong, and assuming that we're still within the length of the sequence, we'll output to the serial monitor what the button that should have been pressed was. If the player is continuing to enter directions after they've got to the end of the sequence, then what we'll do is we'll actually say that they're typing in something that's too long. But remember, we're not actually going to do anything with it quite yet. All we're going to do is set this input correct flag to false and go on to the next step. So we're going to let the player carry on. The time at which we check whether the sequence they've entered is correct or not, well, there's two possible ways in which we check that. The first is if we have defined auto check at the top of the code, and if we've done that, we check as soon as the current step that the player is up to is equal to the total number of steps. So if we're looking for a direction of 8 directions and the player has entered 8 inputs, that's when we check here. And what we'll do is we'll look to see whether the input correct flag is still true or not. If it is, we'll say that the puzzle has been solved. If it's not, we'll say that they've failed to solve it on this occasion. So that's what happens if auto check is defined. It happens automatically as soon as the current step is equal to the number of steps. If auto check is not defined, then we go into this section here instead. And in this case, what we need to do is we need to update the bounce object that's listening to the submit switch and test whether it fell or not. Now notice that before I was checking whether the direction buttons rose, and here I'm checking whether it fell. That's because I have wired the submit switch to the normally open side of the momentary button. I've wired the directional buttons to the normally closed side because they also had those LEDs attached, if you recall, that I wanted to light up when the direction buttons were pressed. I don't have an LED attached to the submit switch. I could add one, I suppose. But that's why this is wrapped the other way around. And depending on how you change your wiring, you might just need to swap your rises and falls around as well. So that's just something to be aware of. Fell simply means that it was at a high voltage of 5 volts and it dropped to 0, and rose meant it was at 0 and it rose to 5. So if that happens, then we need to check two things here when we're not in the auto check mode. We need to check that when the button was pressed, the input sequence that has been entered was correct, and also it is complete. So the current step is equal to the number of steps, and each of those steps was also correct for the sequence. And if that's the case, we call on solve, otherwise we call on failure. So very similar logic here. This one happens automatically as soon as current step is equal to number of steps. This one happens when the submit switch has been pressed, and we also need to check when that happens that the sequence has been completely submitted and submitted correctly. And then we have these two methods, on solve and on failure. So on solve, this is where you can write whatever you want to happen when the lock is unlocked, as it were. So we can print a message to the display. We can also print something to the LCD that the users see. So here I've just put navigation data input correctly. I'm trying to give a kind of a spacey theme here. So this could be a flight path or whatever you want here. If we are using the MP3 player, we can tell it to play the second track, which is going to be some sort of congratulations success audio. And the most important thing is we actually want to make sure we release the maglock, of course. So we will send a low signal just for half a second, and then we'll send a high signal again, which will deactivate energy to the maglock. And we will reset the controller so that it is ready to go again. So we'll reset the current step back to 0, and we'll assume that everything is back to the beginning again. And then players can enter the sequence just as they did the first time and reopen the lock if they want to. If, however, players either enter a complete sequence that contains an error in it somewhere, or if they press the submit button at a point where they haven't entered the complete sequence, then on failure gets called instead. So just as with the on success here, we can print a message to the serial monitor, we can also display a message on the LCD screen, and we can play the third track this time. So this is a sad trombone sound or something like that that lets players know they went wrong. Just as before, however, we reset the current step indicator and we also reset the input correct flag, which means that they can have another go straight away. Essentially, the only difference here is a slight difference to the message that's displayed and the fact that it does not release the mag lock as the success one does. And that's it. So that just about brings me to the end of this video. I hope you found this tutorial useful or informative, maybe even entertaining. Now, obviously the examples I demonstrated here are not drop-in replacements for a padlock like this. They are electronic, they require some programming and also the construction of some hardware around them. But hopefully I've been able to demonstrate the benefits that they have over a simple lock like this. You can add either visual or audio feedback to players at each step of the sequence they enter. You can control the way the lock is actually unlocked at the end. I mean, to be honest, these are quite divisive among escape room enthusiasts anyway. A lot of people really don't like these locks. They can be frustrating to enter. You have to remember to reset them each time and they often gam up. And also the actual aesthetic of one of these locks is very rarely in place in an escape room setting anyway. Certainly in a pirate or a space theme, for example, you wouldn't expect to see a padlock that looks like this. So that little bit of time spent customizing the lock and actually making it part of a physical prop that is styled to your escape theme room, I think actually really does pay off in your player experience. As always, I will upload the code that I demonstrated and the wiring diagrams and more information about the parts I used onto my Patreon account, which I will link in the description below as well. And I want to take this opportunity, as always, to thank all of my Patreon supporters who enable me to create these tutorials each month. Thank you all ever so much. It really does mean a lot to me. If you have any comments or suggestions about this particular tutorial, please do write them below. Or if you want to see more information about any of my other escape room projects that I've created in this channel, you can obviously subscribe here on YouTube, but also do please check out the link to my Patreon. Other than that, I just want to say thank you all very much for watching and I look forward to seeing you next time. Okay, cheers, bye.